So, topic number 3, structure and bonding. What is a bond? A bond is an attractive force that holds atoms together to form a molecule. A bond is an attractive force that holds atoms together to form molecules, such as a chlorine molecules, Cl2. That is just an example. Two chlorine atoms bond together to form a chlorine molecule. So the bond is the force that is holding these two atoms together to form a molecule. When atoms react, when atoms lose, gain or share electrons, they form bonds. Atoms react to attain the noble gases electron arrangement octet stable state, which is 2,8 or 288, so on and so forth. So we have 5 bonds in chemistry. We have the ionic bond, metallic bond, covalent bond, coordinate bond, and van der Waals forces. We also have the hydrogen bond. So we will tackle the first bond, which is ionic bond. So first we have the ionic bond. The ionic bond is also known as electrovalent bond. It occurs between metals and nonmetals, where the metal loses electrons and the nonmetal gain electrons. Now, why do two atoms lose and gain electrons? This is to obtain octet stable state. When these atoms gain and lose electrons and they obtain octet stable state, they form bonds. Such as the example of metal and nonmetal reacting to form an ionic bond is sodium and chlorine. Sodium having an electron arrangement of 281 and chlorine having an arrangement of 287 react to form sodium chloride, react to form two ions, sodium ion and chloride ion. This is also sodium chloride, but we have separated the ions in this compound. So sodium 281 loses this valence electron to form 28 and chlorine gains this electron to form 288. This is how ionic bonds are formed. Another example is magnesium oxide. Magnesium plus oxygen to form magnesium oxide. However, this is O2 negative, but this is 2 positive and this is 2 negative. Why? The two electrons at magnesium is 282 and oxygen is 26. The two electrons that magnesium loses, these two electrons that magnesium loses to form 28 are gained in this energy level to form 28 by oxygen. So that is how ionic bonds are formed. Now the strongest ionic bonds are formed with the metals in the low metals in low energy level, and the strongest ionic bonds are formed between elements at the bottom of group 1 and group 2, which are metals, and elements at the top of group 7 or group 8, which are non-metals. For example, at the bottom of group 1 we have potassium. At the bottom of group 1 we have potassium, which is K, and at the top of group 7 we have fluorine, which is F. Electron arrangement of potassium is 2881, fluorine is 27. What does this form? Potassium fluoride. Why is the bond strongest between these two elements? Because this is the most reactive metal and this is the most reactive nonmetal. Why? Having the largest atomic radius, this valence electron is easily lost to form 288. So potassium ion is 288 positive, and fluorine having the smallest atomic radius easily gains the valence electrons to form 28. So the valence electron is added to form 28. Structure of ionic compounds. Ionic compounds such as sodium chloride have a giant ionic structure. Such structures have many cations and anions. What are cations? We discussed what cations are. Cations are positively charged ions. What are anions? Anions are negatively charged ions. Cations lose electrons. Anion gain electron. So in an element, in metals, the cation is smaller than the element itself. The cation, let's say sodium ion, 2,8, is smaller than sodium itself, 281, than sodium atom. This is ion, this is atom. However, in nonmetals, chlorine nonmetal, the anion has a large atomic radius. Then it is slightly larger than the atom itself, having an electron arrangement of 288. It has gained the electron, hence the weaker nuclear force of attraction. While in chlorine we have 287. How is the structure of an ionic compound? Structure of ionic compound. We can have so let's say we have a cube in this point. I'm not an artist. So in a giant ionic structure, the cations and anions alternate. For example, we have sodium chloride. So here we will have sodium. Here we will have chloride ion. Sodium chloride. Sodium chloride. Sodium. If this is sodium, this is chloride. So the ions alternate in each other in the giant ionic structure. Properties of ionic compounds. They have high melting and boiling points. Properties of ionic compounds. Properties. They have high melting and boiling points. Due to having a giant ionic structure with strong ionic bonds which require a lot of heat energy to break, since they have giant ionic structure with strong ionic bonds which require a lot of heat energy to break. Heat energy to break. Hence they have high melting and boiling points. Property number 2, they conduct electricity in molten or aqueous state but not in solid state. Why? Ionic compounds conduct electricity. We saw alkali metals, alkaline earth metals, they conduct electricity due to presence of delocalized electrons. However, ionic compounds conduct electricity due to presence of mobile ions. The ions such as sodium ion, chloride ion, magnesium ion, fluoride ion, these ions are the ones that conduct electricity. So they conduct electricity in molten state or molten or aqueous state. Aqueous is when they are dissolved in water, but not in solid state. Ionic compounds, I repeat, ionic compounds conduct electricity due to the presence of free or mobile ions. When they are in solid state, the ions are not mobile, hence cannot conduct electricity. But when they are in molten or aqueous state, or they are dissolved in water, aqueous is dissolved in water, they conduct electricity due to presence of free mobile ions. Most ionic compounds are soluble in water but not in organic solvents. This is because ionic compounds are polar. So 3. Ionic compounds are polar. What is a polar substance? A polar substance is a substance that can dissolve in water. For example, sodium chloride, table salt, the salt that you use on your table, it is soluble in water. So it is an ionic compound. It is polar. It is soluble in water but not in organic solvents such as methylbenzene. We go to our second bond, which is covalent bond. How are ionic bonds represented? For example, sodium chloride. So we can use the outermost energy level to represent, or we can use the whole ion. We draw the nucleus, sodium, the first energy level and the second energy level. So 2 electrons in the first and 8 in the second. Mind you, the third energy level is lost. Since sodium lost its valence electron to chlorine, we are looking at the compound sodium chloride. So this sodium ion is positively charged, so you will put it into brackets, positively charged. Positively charged. And next to it you draw the chloride ion, the nucleus, chloride, first energy level, second energy level and third energy level. You draw its electrons, 2. You can, if here you use crosses, then in the other ion you use dots to represent electrons. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Now where is the 8th electron coming from? It is coming from sodium. It has been donated by sodium. So sodium obtains octet stability and chloride obtains octet stability. So this electron in the third energy level is donated over here, and the chloride ion becomes negatively charged because it gains an electron. This is a cation, this is an anion. Sodium loses an electron, chlorine gains an electron. This is how ionic bonds are represented. Another example is magnesium oxide. Another example is magnesium oxide. So we have magnesium oxide, MgO. We draw magnesium. The metal always comes first, followed by the non-metal. Magnesium, Mg, the first energy level and the second energy level. What is the charge of magnesium? 2 positive. Why? Because it loses 2 electrons to oxygen. It loses 2 electrons which are gained by oxygen. So when an atom loses electrons, it becomes positively charged. And you draw the nucleus of oxygen. If in the first one you use crosses, the second one you can use dots. The electron configuration of oxygen is 2, 6. So once you have drawn the 6 electrons in outermost energy level, this atom is not stable. Why? Because it does not have 8 electrons in its outermost energy level. It has 6. How many does it need to gain? 2. Where do those 2 electrons come from? It comes from the electrons that magnesium lost. They are gained by oxygen, and the 2 electrons which of magnesium are gained by oxygen, and the oxygen becomes negatively charged to negative. This is how ionic bonds are represented. Now, a special example of an ionic bond is magnesium nitride. Magnesium nitride. How is magnesium nitride written? Mg3N2. What does this tell you? This tells you that there are 3 atoms of magnesium reacting and there are 2 atoms of nitrogen reacting. So we draw magnesium Mg, we can just draw the outermost energy level with 8 electrons. This is 2 positive. However, in nitrogen, we have nitrogen, the nitrogen is 2 5, so it gains 3 electrons. It is 2 5, so it gains 3 electrons. But magnesium has only 2 electrons to donate. Nitrogen needs to gain 3 electrons to obtain octet stability, but magnesium only has 2 electrons to donate. What do you do in this case? You bring 3 electrons from magnesium and you put the charge of the ion of nitrogen, which is -3, 3 negative. But how many atoms of magnesium have reacted? 3. So you put a 3 outside the bracket. And how many atoms of nitrogen have reacted? 2. 3 atoms of magnesium and 2 atoms of nitrogen. So magnesium losing 2 electrons times 3 loses 6 electrons, and nitrogen gaining 3 electrons times 2 also gains 6 electrons. Hence, this is how the ionic bond is formed. Bond number 2 is covalent bond. This is a bond between nonmetals, mainly nonmetals, and it involves sharing of valency electrons. Involves sharing of valence electrons. Valence electrons are electrons in the outermost energy level. For example, chlorine molecule. We have chlorine molecule is Cl2. So we have 2 atoms of chlorine, Cl, and 8 electrons and 7 electrons in the outermost energy level. Note, you can represent the atom with only the outermost energy level, which is used in bonding, or you can draw the whole atom. So for easier work, I will just use the outermost energy level. We have another chlorine atom. Now the second one with dots. You can't use both with dots or both with crosses, otherwise will be confusing. This is how this chlorine molecule has obtained stability. How? Because as you can see, these are the outermost energy levels represented. Chlorine, how many electrons does chlorine have? 7 electrons in the outermost energy level. 1, 2, 3, 4, 5, 6 and 7. How many does the other? 1, 2, 3, 4, 5, 6 and 7. But the 1 electron in the outermost energy level, it shares with another to obtain octet stability. The electron pair must lie between the nuclei. These are the nuclei. The electron pair must lie between the nuclei so that the attraction forces outdo the repulsion forces of the electrons. As you know, both electrons are negatively charged. However, if they are placed in between the nuclei attract electrons of each atom, hence the atom can be bonded. So another example is water. How is water bonded? We have water is H2O. How many atoms of hydrogen? 2. How many of oxygen? 1. So you draw the oxygen in the middle, or you can just draw the outermost energy level. This is the nucleus, this is representation of oxygen. How many electrons does oxygen have in its outermost energy level? It is number 8, so it has 6 electrons. So you can draw 6 electrons, 1, 2, 3, 4, 5 and 6. Now you join 2 hydrogen atoms to this oxygen. How? You bring the energy level inside the other of the oxygen, and you draw a nucleus and put H, and you draw another energy level, nucleus and hydrogen. Now this hydrogen has 1 electron, so you put a 1, a dot, across a dot, and another one on this side. So and then you bring these crosses in the middle, and this cross in the middle. Note the electrons, the sharing pair of electrons must be written in between the nuclei of the nucleus of the atoms. The nucleus of this and the nucleus of oxygen and the nucleus of hydrogen, the electrons are written in between the space. The representation of, let's say, the chlorine atom was ClCl. A covalent bond is represented by a single dash, a single line. Water, H2O, water is HOH. Why? Oxygen has a covalent bond to hydrogen, and oxygen has another covalent bond to another hydrogen. Carbon 2 oxide has a coordinate bond, carbon and oxygen. Now, when you represent 4 electrons of carbon in the outermost energy level, you have 2 crosses on this side and 2 crosses will share with oxygen. 2 electrons will be used in bonding with oxygen. However, how many electrons does oxygen have in the outermost energy level? 6. So 2 electrons of oxygen will be on the energy level, but 4 electrons will be used in bonding. So 1 of oxygen, a dot and a cross form 1 pair of electrons. Note, a dot and a cross form 1 pair of electrons, which is used in bonding. So 1 electron of carbon, 1 electron of oxygen, 1 electron of carbon, 1 electron of oxygen, and 2 electrons of oxygen which are left. So 1 and 2. How many electrons now each one will have? 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. So this atom has obtained octet stable state. 2 electrons are on the outermost, on the energy level. 2 electrons of carbon are used in bonding. 2 electrons of oxygen are on the energy level, but 4 electrons are used in bonding. So 4 electrons of oxygen combined with 2 electrons of carbon to form 6 and the other 2 8. And carbon gives 2 electrons and gets 4 from oxygen, combines to form 8 electrons in the outermost energy level. Our another example is ammonium. Ammonium ion. Ammonium ion is NH4 positive. This is what brings me to the point where one atom contributes has a lone pair of electrons and another that is electron deficient. So our example is ammonium, NH4 positive. What do I mean by this? We have 1 atom of nitrogen and 4 atoms of hydrogen. So you draw one big atom of nitrogen and 4 atoms of hydrogen. 1, 2, 3, 4. And hydrogen, 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 and hydrogen. Now, in the first hydrogen, how many electrons does nitrogen have in the outermost energy level? Nitrogen is number 7, so it has 5. It has 5 electrons in its outermost energy level. How many electrons do hydrogen have each? So they have 1. 1 electron of hydrogen, 1 electron of hydrogen, 1 electron of hydrogen. We have 1 of nitrogen, 1 of nitrogen, and 1 of nitrogen. Now, assuming this is not there, assuming this hydrogen atom or ion is not there. How many electrons does nitrogen have right now? It has 1, 2, 3, 4, 5, 6. How many do hydrogen have? Hydrogen have obtained duplet state stability. They have 2 electrons. They have gained from nitrogen. But nitrogen still needs 2 more electrons. It still has 2. From these 5, only 3 have been used. 1, 2 and 3. It still has a lone pair of electrons. It still has a lone pair of electrons which it needs to bond. So hydrogen, having a hydrogen ion with no electrons, a hydrogen ion which is positively charged, we say that when an atom loses electrons it becomes positively charged. So a hydrogen atom, when it loses electron, it has 1 electron, but when it loses that 1 electron it becomes a hydrogen ion positively charged, isn't it? So this hydrogen ion will come and attach itself to the nitrogen H, and it will take the 2 electrons of nitrogen. Nitrogen will donate its 2 electrons. This is where this hydrogen positive NH4 is coming from. So first we had NH3, 1, 2 and 3, NH3. But 1 ion of hydrogen came and attached itself to share the lone pair of electrons nitrogen has, which adds 1 hydrogen, which is positively charged. So we have NH4 positively charged, and this is called ammonium ion. It is called ammonium ion. So that is coordinate bond. Bond number 4 is metallic bond. So metallic bond is a chemical bond which holds together atoms of a metal such as sodium, magnesium and aluminium. The atoms are closely packed in a fixed positions in a lattice, which allows them to have delocalized electrons. They have delocalized electrons, hence conduct electricity. We know that delocalized electrons and free or mobile ions are what conduct electricity. Delocalized electrons also determine the strength of the metallic bond. What do I mean by this? I mean that sodium has 1 delocalized electron. A sodium atom has 1 delocalized electron, but a magnesium atom has 2 delocalized electrons, while an aluminium lattice has 3 delocalized electrons. So if we have sodium, this is sodium, we have positive, and so on. And we have magnesium, it is 2 positive. We have aluminium, which is 3 positive. So this is sodium, this is magnesium, and this is aluminium. Note, the number of electrons, delocalized electrons, determine the strength of the metallic bond. So an increase in number of delocalized electrons leads to an increase in metallic bond, and it also increases the conductivity of electricity. What do I mean by this? I mean that aluminium has a stronger metallic bond than sodium. Why? Due to presence of more delocalized electrons. Magnesium has a stronger bond than sodium, metallic bond. Why? Because it has more number of delocalized electrons. Now what does metallic bond determine? Metallic bond determines melting and boiling point. So aluminium has a higher melting point than magnesium. Why? Due to an increase in number of delocalized, because aluminium has more delocalized electrons, hence a stronger metallic bond which requires more heat energy to break. Magnesium has a stronger metallic bond than sodium. Explain. This is because magnesium has more delocalized electrons than sodium, hence a stronger metallic bond which requires more heat energy to break. The delocalized electrons also conduct electricity. The more the delocalized electrons, the better the metal is a conductor of electricity. So aluminium is the best conductor of electricity among these three metals. Why? Since it has the highest number of delocalized electrons, hence it is a better conductor of electricity. When metals are in the same group of periodic table, they will have same number of delocalized electrons. However, they will have different atomic radii. The smaller the atomic radius, the stronger the metallic bond. Hence, sodium has a melting point of 98. Sodium has a melting point of 98, while potassium has a melting point of 68. Why? You cannot say that potassium has more delocalized electron than sodium. No, they are both in group 1, so they both have one delocalized electron. However, sodium has a smaller atomic radius, hence a greater nuclear force of attraction, hence a stronger metallic bond. Metals consist of many metallic atoms arranged in a regular manner in a metallic lattice. They form a giant metallic structure. So if you are asked, why does aluminium have a high melting point? This is because aluminium has a giant metallic structure. Metallic structure is the structure in which the atoms of the metals are arranged with strong metallic bonds which require a lot of heat energy to break. Now our last bond is hydrogen bond. Hydrogen bond occurs between polar molecules that are soluble in water. Hydrogen bond, this is a bond between a hydrogen atom with a small positive charge and a highly electronegative atom with a lone pair of electrons. Highly electronegative atoms are like oxygen, fluorine, chlorine, those with a negatively charged, let's say Pru negative, negative, chlorine negative. And the positive charge of hydrogen atom is represented with an S. It is a symbol like an S, but its tail is joined to the stomach and it is positive. And the negative charge of the electronegative atom is S negative. So what you don't have to know all this. What you have to know is hydrogen bond occurs in polar molecules, in polar substances that are soluble in water. In water, the hydrogen atoms are partially positive, while oxygen atoms are partially negative. Same in HCl. So I have given you an example of the hydrogen bond in HCl. Hydrogen to chlorine, chlorine to hydrogen. This is the hydrogen bond joining two molecules of hydrochloric acid. Two molecules of HCl are joining due to a hydrogen bond between H and Cl. Hydrogen is I'll just call it S, but it's positive. Chlorine is negative. Hydrogen is positive and chlorine is negative. What does this mean? This means that hydrogen is partially positive. This is symbol for partially positive and this is symbol for partially negative. So partially positive, partially negative, hydrogen bond, partially positive and partially negative. Hydrogen bonds are stronger intermolecular forces than van der Waals forces. Hence, the polar molecules have a higher melting point and boiling point than molecules only with van der Waals forces. We go to van der Waals forces and you will know the difference what I mean. After the hydrogen bond, we have van der Waals forces of attraction. What are these van der Waals forces of attraction? They are weak forces in substances that have a simple molecular structure. Which substances have a simple molecular structure? Substances which have covalent bonds, such as chlorine. Chlorine is covalently bonded, but it has weak van der Waals forces of attraction. Same with bromine. We are told they depend on molecular mass. What is molecular mass? Molecular mass depends on atomic radius. So, for example, the atomic radius of bromine is larger than the atomic radius of chlorine, due to an increase in atomic radius. Hence, an increase in molecular mass. Bromine has more molecular mass than chlorine. Hence, more van der Waals forces of attraction, which require more heat energy to break. What do I conclude from that? I conclude that bromine has a higher melting point or a boiling point than chlorine. I repeat, atomic radius, an increase in atomic radius, a greater atomic radius leads to increase in molecular mass. Molecular mass is what determines van der Waals forces of attraction. The more the molecular mass, the more the van der Waals forces of attraction, which require more heat energy to break, hence the higher the melting and boiling point. Atomic radius increases molecular mass, hence more van der Waals forces of attraction. We go to the structures. So we have the 4 structures in chemistry, which are simple molecular structure, giant metallic structure, giant ionic structure, and giant covalent structure. So we first have the simple molecular structure. This is formed by covalent bonding in molecules. The molecules are held together by weak van der Waals forces of attraction. Now the covalent bonding is for atoms. Covalent bonds are for atoms, while weak van der Waals forces of attraction, van der Waals forces, are for molecules. So melting and boiling points, heating breaks the weak van der Waals forces of attraction and not the covalent bonds. I am reading this for you and I am explaining. In iodine, the atoms are held by covalent bonds which are strong, but the molecules are held by van der Waals forces which are weak. Melting and boiling points break the van der Waals forces and not the covalent bond. So the atoms are held by covalent bonds, but the molecules, when they exist in pairs, I2, a molecule, iodine molecule, is held by weak van der Waals forces of attraction, which require less heat energy to break. Properties of compounds with a simple molecular structure. 1. They are insoluble in water except the polar ones, which are soluble. And secondly, they do not conduct electricity due to lack of mobile ions. They do not dissolve in water, hence they lack mobile ions to conduct any electricity. They have low melting and boiling points. Why? Because they have a simple molecular structure. This is the explanation. They have a simple molecular structure with weak van der Waals forces of attraction, which require less heat energy to break. The other structure we have is giant metallic structure. Giant metallic structure. Metallic structure is formed by a lattice of metal cations, positive centers surrounded by delocalized electrons. The ions are closely packed. So we saw in a sodium, it has delocalized electrons and it is closely packed. Elements with metallic structure have the following properties. 1. They have high melting and boiling points. Why? Because they have delocalized electrons, hence a strong metallic bond which requires more heat energy to break. They have high electrical and thermal conductivity. They conduct electricity. They are good conductors of electricity. And thermal conductivity. They conduct heat also. They have high density and are very strong, ductile and malleable. Malleable, we said in previous lessons, can be hammered into sheets, and ductile into wires. Our next is giant ionic structure. Before that, we can say uses of metals, although not necessary, we can just write them down. We have aluminium and copper are used to make electric wires due to good electrical conductivity. Aluminium and copper are used to make electrical wires. And 2, they are used to make cooking utensils due to high Thermal conductivity. Cooking utensils, since they are good conductors of heat, such as sulfurias, aluminium sulfurias, good conductors of heat due to high thermal conductivity. Our next structure is, that was our second structure, giant metallic structure. Our third structure is giant ionic structure. Giant ionic. As the name suggests, giant ionic structure, we know it is in ionic compounds, and ionic compounds are in molten or aqueous state and conduct electricity. So the structure are formed by ionic bonding as a result of close packing of ions. So when ions bond, they form a giant ionic structure. They are closely packed. They have following properties. They have high melting and boiling points. High melting and boiling points. Why does a giant ionic structure or ionic bond have a high melting or boiling point? Because it has a giant ionic structure with strong ionic bonds, which require more heat energy to break. Secondly, they conduct electricity. This is number one. Number two, they conduct electricity in, mind my words, they conduct electricity in molten or aqueous state, but not in solid state. Sodium chloride, or common salt, does not conduct electricity when it is salt in solid state, but when it is dissolved in water, it has presence of mobile ions. Why does it conduct electricity in molten or aqueous state? Due to the presence of mobile ions. And it does not conduct in solid state due to lack of mobile ions. They dissolve in polar solvents as they consist of charged ions. So 3, they are polar. They dissolve in water to form solutions that conduct electricity. Our last structure is giant covalent structure, number 4. Also known as giant atomic structure, because it is covalent bonds between atoms. Giant covalent structure. So this is covalent bond between atoms, covalent or atomic structure, giant atomic structure. Giant covalent structure is formed by covalent bonding. Carbon forms two pure substances. So now we will look at allotropy. Under this giant covalent structure, we will look at a subtopic known as allotropy. So before we look at allotropy, we have these 3 elements, compounds that have giant covalent structures, which are silicon 4 oxide, and carbon. Now allotropy will come under diamond and graphite under carbon. So we can look at the what is it called, properties of giant covalent structures. They have high melting and boiling points. 1, high melting and boiling point. Reason: giant atomic structure, giant covalent structure, strong covalent bonds, require more heat to break, more heat energy to break. So in ionic structures, we saw a giant ionic structure with strong ionic bonds which require more heat energy to break, hence it has a high melting and boiling point. In covalent structure, the explanation is the same, only that covalent replaces ionic. So it has a giant covalent structure or a giant atomic structure with strong covalent bonds which require more heat energy to break. 2, they are poor conductors of electricity except graphite because they lack delocalized electrons. 2. They are poor conductors of electricity. Poor conductors of electricity. They lack delocalized except graphite. They are insoluble in water and organic solvents. Number 3. So they are nonpolar. Polar is a substance that is soluble and non-polar is a substance that is insoluble. So you can just say they are non-polar, or they are not soluble in water. They are non-polar and insoluble in organic solvents. Organic solvents are learnt in organic chemistry, but examples are methylbenzene, organic solvents. And now we look at allotropy. Under this giant atomic structure, we have allotropy. What is allotropy? Allotropy is the existence of an element in more than one crystalline form in the same physical state. This is the existence of an element in more than one crystalline form in the same physical state. And an example of allotropy is carbon. Carbon exhibits in two different crystalline forms, which are: 1, we have diamond, and 2, we have graphite. So we will see the differences in these crystalline forms and their uses. So allotropy is the existence of an element in different crystalline forms in the same physical state. Physical state is like solid, liquid, or gases. So in the same physical state, diamond and graphite are both in the same physical state. They are both solids, but they are existing in different crystalline forms, and they are forms of carbon. So we will first look at diamond. It consists of carbon atoms in which one carbon atom is covalently bonded to 4 other carbon atoms. All valency electrons are used in bonding, hence none is left as a delocalized electron. Therefore, diamond is a poor conductor of electricity. Also, diamond is hard. We will look at that. So first, diamond is a poor conductor of electricity. Why? Because one atom of diamond covalently bonds to 4 other atoms. So it bonds with all atoms, hence leaving no delocalized electrons. One carbon atom covalently bonds to 4 other carbon atoms, hence there is no delocalized electrons to conduct electricity. Diamond is a poor conductor of electricity. Another property of diamond is that diamond is hard. This is due to the giant atomic structure in which the strong covalent bonds are octahedrally arranged, hence making diamond compact. So diamond is hard. I think diamond is the hardest element in the world, and if not the hardest, among the hardest. But diamond is hard. Why is diamond hard? Because it has a giant covalent structure. It has a giant covalent structure with strong covalent bonds. But why is it hard? These covalent bonds are octahedrally arranged. Octahedrally octahedrally arranged, hence making diamond compact. It is compact, hence it is hard. Giant covalent structure with strong covalent bonds. The covalent bonds are octahedrally arranged, hence making diamond compact. And don't forget, in diamond, one carbon atom covalently bonds to 4 other carbon atoms, hence it does not leave any localized electrons. Therefore, diamond does not conduct electricity. Diamond has a high melting point of 3700 degrees. 3700 degrees high melting point. Due to the giant atomic structure with strong covalent bonds. Giant covalent structure or giant atomic structure with strong covalent bonds. It's the same explanation. Uses of diamond. So we saw diamond has a giant atomic structure with strong covalent bonds that are octahedrally arranged. They are arranged in an octahedral structure, hence making diamond compact. What are the uses of diamond? Diamond is used to make drills. It is making ornaments because it is shiny, and used to make drills, cutting metals because it is very hard. It is used to make drills, cutting metals because it is very hard. 2. Diamond is used to make ornaments because it is shiny when polished. These are the uses of diamonds. We go to the second allotrope, which is graphite. So graphite is different than diamond, is different from diamond, and it occurs in a different crystalline state. Graphite in graphite, one carbon atom is covalently bonded. One carbon atom is covalently bonded to 4 other carbon atoms. Hence it has a delocalized electron which conduct electricity. In graphite, we saw carbon has 4 electrons in the outermost energy level. In diamond, each connects to another 4, hence there is no delocalized electron. But in graphite, one carbon atom covalently bonds to another 3 carbon atoms, hence there is one valence electron, one delocalized electron which conducts electricity. Therefore, graphite is a good conductor of electricity. Graphite atoms are covalently bonded. But in diamond they are octahedrally arranged. In graphite they are hexagonally arranged. Hexagonally layers held by weak van der Waals forces. The layers slide over each other when pressed. when a pencil lead is made of graphite, when you sharpen it, why does it become sharper? Because the layers, when pressed, they slide over each other, so one layer is removed. So covalently bonded hexagonal arranged, the layers are hexagonally arranged. The layers are hexagonally arranged in hexagonal structure held by weak van der Waals forces. The layers slide over each other when pressed. That is why graphite is soft and slippery. Diamond is hard and compact, whereas graphite is soft and slippery. Uses of graphite: making pencil lead when mixed with clay because it is slippery. I just said graphite is used in making pencil lead. Making pencil lead. And secondly, it is used in making electrodes for dry cells because it is a good conductor of electricity. 2. Making electrodes for dry cells because it is a good conductor of electricity. And with that, I think we have marked the end of our topic, structure and bonding. Thank you all for watching. I hope you have understood. Any questions can be dropped in the comment box. I will clear them. And for now, we will call it a day. Take care. Goodbye. See you. Thank you for watching.